So we learned in the previous lesson that it's possible for the universe to actually spontaneously form particles by borrowing energy from the universe, as long as it returns that particle within a very short period of time. How short depends on how much energy it borrows to create the particle. The more massive the particle, the more energy borrowed, the shorter lifetime that particle has. That doesn't violate the uncertainty principle. Now, we can take advantage of this creation of particles from energy and actually create our own energy sources. Rather than relying on the vacuum of the universe where there is no energy and a virtual particle pops into existence and then pops out of existence in a very short period of time, if we provide the energy to the universe, then a particle can pop into existence and stick around. So if we create energetic enough collisions, particles can pop into existence depending on how much energy we create in that collision. The mass of the particle depends on the energy available. The more mass of the particle we want to create, the more energy in the collision we need to provide. Now, there are two ways of providing energy in a collision. One is by colliding matter and antimatter, and we'll talk about that in a bit. And the other is just kinetic energy. Smashing two particles together near the speed of light creates a tremendous amount of kinetic energy that can be used to generate this energy soup can then be used by the universe to spontaneously create particles. Now, it's really not possible to determine exactly what particle is going to be created. Once you give the universe a big pool of energy, it can randomly create different types of particles. And there's no way that I'm aware of to force the universe to create a very specific type of particle. You just have to give it enough energy and hope that that particle appears. Now, the more energetic the collision, the more mass of the particle or particles you can create. To create these energetic collisions, physicists have designed particle accelerators. These are devices that take usually strong electric and magnetic fields to accelerate charged particles to near the speed of light and then smash them into either a stationary target or smash them into an opposing beam of particles traveling in the other direction. This collision of beams creates an area where the collision occurs of very high energy. That high energy can be used then to create, by the universe, to create these random particles. This is not a chemical reaction. This is not even really a nuclear reaction, which follow very specific guidelines. This is just creating a swamp of energy and allowing then particles to form out of this energy swamp. And there are three major types of colliders. There are a bunch of different subsets to these, but your book goes over these main three. There's a simple electron gun called the Van de Graaff, and an example of that is shown here on the right. An electron gun is just exactly that. It's accelerating electrons, basically using electric and magnetic fields, to create an electron beam that then collides with a stationary target. The electron gun principle is actually used in old CRT televisions, old cathode ray tube televisions. The big, massive televisions that your parents or grandparents might still have hidden away somewhere in their house. Or if you're like my grandparents, they actually had their flat screen TV sitting on top of their old box furniture TV, old CRT. Most flat screen TVs are flat screen now, CRTs are hard to come by. But those old TVs use this electron gun principle. Then you end up with a cyclotron. A cyclotron, shown here on the right, uses two opposing metal bowls called Ds, because it looks like the letter D forwards and backwards. The Ds, when a particle is inside the Ds, it is shielded from the electric field and is accelerated by the magnetic field, which spins it around. And then as it crosses through the Ds, the charge on the metal plates is flipped, causing the electron or proton or whatever charged particle you're accelerating to jump and accelerate across the gap, and then turn around, accelerate across the gap, turn around. So the path of the electron, in this case, we'll assume it's an electron, gets larger and larger and larger every time it goes around one of the Ds. But of course, you don't want that electron to be blocked by anything, so those Ds are typically evacuated. They're in a vacuum, so the particle is less likely to hit air particles around or other neutral particles. That can accelerate charged particles. The problem is that to get something going really, 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 really fast, you would need enormous Ds. You need enormous metal bowls for a synchrotron. And creating a vacuated chamber of something that large isn't practical. So we take it to our third type, most modern type of particle accelerator called a synchrotron. Now, synchrotrons, Fermilab near Chicago is a synchrotron. The CERN facility in Switzerland is a synchrotron. This uses a fixed ring size and varying magnetic fields to accelerate particles up to incredibly high speeds and then smash them together. Now, the more sophisticated particle accelerators can actually create matter-antimatter collisions. That's literally taking a bit of antimatter, creating a bit of antimatter, colliding it with a bit of matter. So not only does the kinetic energy of the collision go into it, but when the matter and antimatter destroy one another, that produces energy as well. So you can get very high energy collisions. The higher the energy of the collision, the more mass of the particle you can create. And you use then a bubble chamber or cloud chamber in the particle accelerator to measure the existence of these particles that appear. What is their motion? What is their charge? Are they affected by a magnetic field? What's their mass? And so on. And you can get information from these exotic particles to create a list of all the different types of particles in the universe. So we'll be covering that list in the next few lectures.